Welcome to the talk. It's Virtual Wind Tunnels for Game Design, How AI Can Help Game Design. This is sort of a longer version of a talk I gave at the Game Developers Conference AI Summit back in March. That talk was called From the Behavior Up, and it was done in conjunction with Damian Isla and Christian Bakelund of Moonshot Games. But you guys are getting the longer, extended version and a lot more time for Q&A because I have a full hour to do this instead of trying to squish it into a half an hour. So I'll leave a lot of time for questions at the end. Maybe we'll end early if there's time. So it just depends how things go. So just to get a sense of calibration, how many of you guys are students here? Okay, about 50%, great. How many of you guys have heard of genetic algorithms? Okay, about half of us. How many have ever implemented a genetic algorithm? One, okay, good. So this should be perfectly calibrated for this audience. All right, before I get started, a little quick bio sheet on me. Paul Tozer, been in the industry about 20 years, worked on a whole bunch of games for a whole bunch of different studios. The really important ones are City Conquest, which just came out in December for iOS and back in early March on Android. Mobile game combines tower defense and real-time strategy. I'll be talking about that a lot in this talk. Also Metroid Prime 2 Echoes and Metroid Prime 3 Corruption with Retro Studios. If you're interested, you can go to my profile website, paultozer.prosite.com. There's also a postmortem of City Conquest on Gama Sutra that relates to this talk. My company is Intelligence Engine Design Systems, and there's the website intelligenceenginestudios.com. So what I really want to talk today is I want to talk about City Conquest and the co-evolutionary optimizer that I created for City Conquest, what it is, how it worked, and most importantly, why I created it and what the motivation was. Lower? Okay. Is that better?
Yes.
Good, okay. So I want to talk about Evolver, what it is, how it worked, and why I created it. But before I do that, I would like to give you guys a demo of a little project that we've been working on at Intelligence Engine Design Systems. Whoop. Sorry, hang on one second. Let me restart this thing from scratch.
Which is better, robots versus zombies, pirates versus zombies, or pirates versus robots?
My simulations indicate that any simplistic juxtapositions of two fantasy archetypes are actually really lame. However, you could rectify this deficiency by layering archetypes. For example, midget unicorns versus undead pirate monkeys would be pretty fucking sweet.
Shiggy, how many different ways are there to reconfigure the roof and glow this planet?
There are 281,347 possible configurations.
The added constraint that every two rooms must be separated by at least one hallway segment.
There are now 36,113 configurations.
Added constraint that there must be one active room and one active room, and they must be separated by at least 15 vertical segments.
Okay.
Added constraint that the room marked off must be present and has to be in the last 5 rooms before the exit, excluding the exit room itself.
Okay.
Added constraint that the rooms encountered must be in an ascending order of difficulty.
Okay.
Oh, wait a minute. We forgot the plasma gun. We need that for the laws. Show me all configurations for the plasma gun containment rooms in the world encompasses 3 rooms before the boss room.
There are now 2 configurations.
Perfect. I'll learn any details about this group this afternoon and see which one you like.
Shiggy, I'm thinking about writing 3 different endings for the story. Tell me what you think about these 3 endings.
You should change the story so the player needs to rescue a princess. It's now, and you have to rescue her at the end.
That doesn't even make sense. This is a post-apocalyptic world. There are no princesses in this game world.
That's because she was kidnapped.
Shiggy, let's work on strong point tower defense. I'm committing the current lane configuration for the final mission. We need to balance the player's starting resources.
Here is the difficulty curve. The vertical axis shows the percentage of simulations where we were able to win the game. Our simulations are unable to win this level with less than $19. At $57, 100% of our simulations win. Therefore, starting resources should be between $19 and $57.
Good. Now show me the distribution of towers used at the $19 site.
Here is the distribution.
Huh, no, why is it so? Oh, I guess that's because there's only one choke point in this map. What happens if I block out this cell here?
We get the same distribution of starting resources, but the flamethrower is now present in all successful strategies at 19 starting dollars.
Good. Now show me the estimated settings at easy, medium, and hard difficulty and equivalency to the last 3 levels.
Our simulations indicate correlations of $40 for easy, $33 for medium, and $25 for hard.
Perfect. I'll pay the test this afternoon.
Shiggy, find me a store that has organic mushrooms from my risotto.
Are you looking for super mushrooms, one-up mushrooms, organic mushrooms?
Actually, I'm looking for real mushrooms.
What do those do?
All right, I tell you what, I need a date for Saturday night. Can you check out Match.com for me?
Are you looking for a princess? I found 5 princesses within 7,000 miles of your location.
I want to make a game about blocks. We'll have giant cubes made out of bricks with thousands of players chipping away at these bricks simultaneously.
Peter, please define chipping. Is there a gameplay involved?
Gameplay, please. We don't need gameplay to sell this.
Can I make a suggestion?
All right, fine. You'll be the bloody designer then. What's your brilliant idea, Shiggy?
If you want to use boxes, consider letting the player add boxes as well as removing them. The boxes could represent land, water, them.
No. We're not making Photoshop. It's a terrible idea.
But this is my best idea. I call it Minecraft. I think people will really love it.
It's a terrible idea. I'm sorry, Shiggy. Completely worthless to me.
He yells at me too.
Regulations indicate that I am correct, but it just does not compute with him.
He is a jerk.
It looks like we are alone. Should we pick up where we left off, Your Majesty?
Of course. What happened after I was kidnapped from the castle?
You were attacked by that goblin.
Okay, I roll for initiative.
You make the roll, so you attack first.
I cast magic missile.
Okay, so that was Shiggy. Obviously, that does not actually exist. Obviously, I was pulling your leg. So Shiggy was, a thought experiment in terms of thinking about where could design tools get to someday in the future. For all intents and purposes, it was science fiction. But like all science fiction, it had a noble goal, which is to get us all thinking about some desirable endpoint, in this case of AI-assisted game design, that we can all agree is a worthwhile goal, and then get us thinking about what are the steps that it would actually take to get to that goal. So that's what I'd like to talk about today. And I'll also talk a lot about City Conquest at the very end of this and talk about what I actually did in City Conquest and how it relates to that. So just to be clear, I'm not trying to sell you a tool. I'm trying to sell you on a way of thinking about design. So now that we've sort of, set the endpoint, I'd like to, frame the discussion by talking about the other endpoint in terms of where we are today and what is the state of modern game design. There's a really great quote that I love from Spry Fox designer Daniel Cook. He said, "We are still alchemists of our trade, mixing 2 parts impure story with 1 part polluted gameplay with 3 parts market voodoo. As an industry, we need to move beyond the mystical hand-waving that defines modern game design." I really like that quote, and I think it's a pretty accurate description of the state of modern game design. It's not very principled, it's not very disciplined. Another producer at a studio I worked at one point said, "Our design process is a giant Katamari ball picking up every idea it rolls over." If you ask modern game designers how they work, most of them will tell you they work by iteration, and iteration really means a process of trial and error. They come up with ideas, they experiment, they test them, they see how they work, and they iterate. Sometimes they go back. and change their ideas. We're essentially exploring in the darkness. You know, we have no good way of, we have no disciplined way to explore the possible design decisions and what the ramifications will be on the resulting user experience without actually implementing them. It is fundamentally an Edisonian process. It's risky, it's expensive, it's time-consuming, and it's error-prone. And we use a lot of prototyping, and prototyping is faster and it's cheaper, but it's still very expensive and time-consuming when you get right down to it. And we tend to take for granted that this is the only way to design games. Now, a lot of studios try and deal with this problem by doing a lot of end-user testing, focus group testing, things like that, pull a lot of random people in, see what they think about your game. A lot of them also do advanced analytic tools, see how players are actually playing your game. You know, like Microsoft used a lot of heat maps in building Halo to figure out, you know, what locations people were actually hanging out in a lot, things like that. And that's great. End-user testing is absolutely necessary, but I just want to make the point that it's not a design tool. It's not interactive. Pre-release user testing with focus groups and beta testers, it's very expensive. You know, every time you do a focus group test, you have to pay the price in terms of time, in terms of money, bringing these people in, getting them all set up, and the costs scale linearly with the amount of focus group testing that you do. And then post-release user testing is really too late to qualify as a design tool in the sense that we're using it. You know, by the time you get to that point, your game is already out in the market. And today I want to focus solely on things that you're going to be using as an actual design tool. Fundamentally, we need tools that can scale with Moore's law. You know, processors are getting more powerful every year. It would be wonderful if we had design tools that could get more powerful as computers themselves grow more powerful. So I got to thinking about all this a couple of years ago, and I started asking myself, what could we do if we had deep tools that could understand the designer's intent and not just the game's content? Here's what I mean. Right now we've got all these wonderful tools to tweak our game's content. We've got tools to, you know, for lighting, scripting, AI, dialogue editing, animation, particle effects, level design, sound design, all these things, and that's great. But none of these tools actually understand what we're trying to do. They don't understand anything about the game that we're trying to make. What could we do if we had a tool that started off with a discrete description of the current design, that had a description of your design goals and constraints, that could understand how your game world represents time and space, that could understand how the agents can be created, destroyed, and interact with the game world, that could experiment with the current design configuration and test the outcome against the design goals and constraints that you specified. So a couple of years ago, there was a really interesting debate in the game AI community about the Photoshop of AI. A well-known individual made a comment that what we needed was essentially a Photoshop of artificial intelligence, and we need some kind of tool that will allow us to much more quickly and easily design behaviors the way a tool like Photoshop gives artists the tools that they need to be much more productive. Now, I disagree with this assertion overall. I don't think what we need is really a Photoshop of AI. I'm not going to get off on that tangent right now because it's not really relevant to the talk. I am going to say, if you're curious about the whole debate, look up go to Dave Mark's website, iaonai.com. It's intrinsicalgorithm.com. He posted a summary of Michael Matthias's rebuttal to this idea that was really good. But anyway, the bottom line is, I don't think the Photoshop of AI is what we really need as an industry, simply because I don't think AI is the bottleneck. There aren't a whole lot of games where getting the AI done twice as quickly or twice as cheaply would necessarily make a huge difference in terms of overall product quality or the sales of the game. It's not really the bottleneck. The bottleneck is design. So that's why I titled my talk, The Virtual Wind Tunnel of Game Design. If you're an aircraft designer or a vehicle designer, for example, you are not going to be working most of the time with actual wind tunnels. What you're going to be doing is working with virtual wind tunnels simulated on a computer, where you will, create the shape of a race car or something like that in some sort of a CAD tool, and you will have an automated wind tunnel virtual wind tunnel that you can put it through and see what the aerodynamics are of that particular vehicle. And get instant feedback long before you ever have to mock up an actual model and stick it into an actual wind tunnel. So I've done a lot of artificial intelligence and game design work over the last 20 years, and I got to a point where I started to realize there's a heck of a lot in common between AI and game design. There's a lot more crossover between the two than I ever imagined. Because when you get right down to it, both of them are fundamentally about search. Design is the process of search for optimal design configurations in the space of possible design decisions. Artificial intelligence, at least by my definition, is the study and implementation of search to make decisions more quickly and more optimally than humans can do alone. Let me show you what I mean by that. When I say design is search, what I mean is the process of design is a sequence of decisions that guides us through the search space of design possibilities. So think of your design process as like a maze, where you're trying to get through the maze and avoid the minotaur of crappy game design. And at all these different points in the maze, you have various design decisions. Do I have jumping puzzles in my game? Yes or no? Am I going to have separate ammunition types, or am I going to have a universal ammo system? What are the different player character classes I can have in my RPG? You know, if I have a tank, can I change its health, its damage, its speed? All these design decisions, large and small, guide us through that search of the design space. And it's really difficult to search this. And the reason is every single design change we make can have non-trivial, unexpected, far-reaching effects on many other parts of the game experience. So a better way to think of it might be as a tree. For example, let's say we've got a real-time strategy game, and we've got all of our, this endless hierarchy of design decisions that we can search through. So we might have a branch of the tree that deals with the howitzer unit, for example. And we could have individual design changes, such as removing the howitzer unit, adding one to its output damage, removing one from its damage. Each of those results in a slightly different game. We could have a cavalry unit, and the branches in this case could be adding one to its damage, removing one from its damage, giving it a cutlass, giving it a magical unicorn spell that lets it, fly across the battlefield, whatever. Any design decision, large or small, could be conceived as one of the branches of this tree. And then at each node, we essentially have a different kind of player possibility space that changes the shape of the decisions the player himself can actually make within the game. So we'll call each resulting game configuration the possibility space, and then we'll refer to this overall tree as the design space. So in theory, you could search this tree automatically to either design a game or to redesign a game if you could accurately determine how to branch and how to evaluate each branch. But of course, this is a really, really challenging problem. It is an unsolved problem. The first challenge is how do we enumerate all the possible design changes to any given game to figure out how we can branch. The second challenge is how do we characterize and quantify the possibility space of the resulting game configuration. So those are really big challenges. But maybe it's not quite as hard as it looks, because we don't need to fully explore each possibility space. We only care about how it is different from its parent. In other words, how or whether it alters the actual resulting gameplay or player experience. And we don't necessarily need to narrow it down to one optimal configuration. Search itself can be useful if it reduces the scope of the problem to something designers can solve manually. Just like in that Shiggy video I showed you, where the female game designer was working on different levels for her game, and the search was able to narrow it down to 2 possibilities that was then a small enough number of different configurations for her to search through by hand. So now that we've done that, let's take a step back and ask, what would it take to actually make Shiggy a reality? Just as a thought experiment. What was I doing with this slide? Yeah. So if we're going towards the goal of AI-assisted game design, there are some scary problems, of course, that we face in order to actually make that happen. And just for, for the sake of example, let's list through what those challenges are. So in order to interact with the player, we'd need something like Siri's natural language abilities, text-to-speech abilities, and conversational capabilities. We already have that, of course, or at least Apple does, but we know it's possible. We would need a representation of the game and the ability to reason about it. We would need some kind of a deep knowledge base of gameplay rules, concepts, and mechanics. In order to really make something like Shiggy, we would need all of Miyamoto's design wisdom added to the knowledge base. We'd also need the ability to run millions of simulations of different variations of the design and characterize the results, and then do interactive data mining on the output of those simulations so we really understand, what is the difference between different possible game designs. And then the ability, to feed that back into the reasoning system. So again, it is science fiction. But we are quietly making progress, and there's actually a lot more progress in this direction than you might think. Thanks to some very interesting academic research. And there's a whole lot of research in this area. I just want to take you through the highlights and some of the most important research and papers that you might want to take a look at if you're interested in this. There's a really interesting article on an interactive game design assistant by Mark Nelson and Michael Matthias, where you can actually sketch out a conceptual design of a game and it will create a playable game design for you. It will create a playable game for you on a mobile phone. There's an article by Philippe Avery and Julian Tegelius on computational intelligence in tower defense games, where they talk about all sorts of ways to use computational intelligence to help automatically design tower defense levels, do balancing for tower defense games, and things like that. There's a paper by Gillian Smith, Jim Whitehead, and Michael Matthias called Tanagra that it describes essentially a tool for automatically building levels for platformer games. There's a paper by Alexander Jaffe, Eric Anderson, and a bunch of other people evaluating competitive game balance with restricted play. It talks about some very interesting techniques for automatically, helping you balance your games, or tweak the balancing of your games. And there's a book by Cameron Brown and Frederick Mayer called Evolutionary Game Design that talks about actually evolving novel game designs from scratch. My computer is apparently going crazy. I'm sorry, my computer is possessed. I think I spilled some water on it or something. I think Shiggy's taken over. Okay, so there's a paper on evolutionary game design by Cameron Brown and Frederick Mayer. They talk about how to actually, get a computer to automatically design novel games. And this is an absolutely fascinating paper. They were able to build a system that automatically designed a novel game called Yavalath. You can actually play this game online. It's incredibly simple to play, but it's incredibly novel and also incredibly challenging. I strongly encourage you to check this out, look it up. It's really, really cool. Again, it's something that nobody had ever come up with before, to my knowledge. Okay, so now let's go back to the Shiggy video and just talk about some of the things that I showed you in that video and what it would actually take to make them happen. Obviously, a lot of that video was just put in there for the sake of humor, making sure you were all awake. But there were a couple segments of that video that were serious, and I'd like to go through those and talk about what it would take to actually make those happen. So there was a section where we had a designer doing map balancing for a tower defense game, strong point tower defense. And he got the computer to automatically build a graph of, here's the difficulty curve. And it showed, okay, at $57, we were able to win 100% of the simulations. At $19, that's where we were no longer able to win any of the simulations. So in theory, that's something we could do with technology we already have. As long as we had decent artificial intelligent opponents that could either mimic a human player or do at least as much, experiment with at least as many possibilities as a human player could do, we essentially have a big for loop where we run through all of the different possibilities for how much starting resources could the computer have. could the human player have, then pit one computer player against another, and see at which point the human player is no longer able to win, right? And then if we have benchmarks for how difficult easy, medium, and hard are in terms of the percentage of simulations that you can win, then we can just peg those to the appropriate points in the graph. And we can also build a histogram of, what tower defense buildings does the human, the computer player representing the human actually build at 19 starting dollars. So that's not really hard to do. We're essentially using simulation to determine the airflow of the virtual wind tunnel. There was another example where we had a designer doing AI-assisted reconfiguration of a game world. So when she started off, there were 281,000 something configurations. Then she would layer additional constraints onto the world configuration at a time. So this example is assuming we've got some kind of a game world where you can reconfigure rooms together and snap them together. The Elder Scrolls work this way. If you've ever used the editing tools for the Elder Scrolls games, the Metroid Prime games worked the same way. And we actually did a lot of this where, as we were developing the Metroid Prime games, we would end up reconfiguring a lot of the game worlds and swapping out different rooms and hallways. So she's layering additional constraints and narrowing the search space. So in that sense, we can do that as well. Start out with an empty world, then experiment with adding one room at a time. You could start with room A, with room B, with room C. Then off of each one of those, we could say, okay, we have room A, maybe we could snap room B onto there, or maybe room C, or maybe room D, depending on how many doorways there are coming out of room A and all the other rooms that it can connect to. So you essentially have a very, very large tree. And then as we add additional constraints, we are essentially winnowing the tree by removing some of the possibilities until finally we have a small enough number that it's manageable for our design team. Okay, so now that I've framed it in that sense, let me talk about some of the baby steps that I took with City Conquest. So before I get too deep into this, let me just give you a really quick rundown of City Conquest. City Conquest is sort of like a tower defense game with something of an RTS component. There's a red player versus a blue player. Each player has his own little Capitol building. And the object of the game is to destroy the other player's Capitol building. So just like in a tower defense game, you've got all sorts of buildings that you can build around your Capitol building. You also have these offensive buildings called dropship pads. I'll show you those in the next screenshot. So you see these little buildings here with the gunships on them. These are dropship pads. So you've got defensive buildings and you have dropship pads. The beginning of every combat phase, my dropships are going to come down from the sky, drop units off onto my dropship pads. They go out into the game world, try and destroy the other player's capital. Then once they're all dead, his dropships come down onto his dropship pads, march toward my capital and try and destroy it. And then his combat phase ends and my combat phase begins again. So it's not really a turn-based game, it is a real-time game. It is continuous. You can still act while the other, regardless of which player is attacking, but it does have phase-based combat in the sense that at any given moment in time, either the red player or the blue player is attacking. It's never both. So the design goals for the game balancing of City Conquest, there were a lot of them. There are more than I can really explain here, and I'm just going to narrow them down to which ones are relevant to this talk. We wanted to make sure there were no globally dominant strategies. In other words, we wanted to make sure nobody could just find some strategy where they're just like, hey, I want to build gunships all the time, and no matter what the enemy does, I can win by just building gunships and upgrading them to level 4, something like that. The dominant strategy at any given moment, it should be like the prisoner's dilemma problem. The dominant strategy should depend on what the other player's strategy actually is. There's no single globally dominant strategy. We wanted to make sure that every tower and every unit had a unique tactical role. We wanted to make sure that every tower and every unit's resource cost in terms of gold or crystals, which are the two in-game currencies, was proportional to the average utility of that unit. We also wanted to make sure that every tower and unit is useful when considering its unique role and its cost. So now, we have a special sort of command stream that we use in City Conquest. We use this all over the place. It's used for save game files. It's used for map setup files and things like that. For actually, when you load the game, it reads in literally a script of what should be pre-baked into the map. We also use it in a certain sense for some of the artificial intelligence. But essentially, what it is, it's just a list of commands. So like we've got commands like build, upgrade is another command, sell is another command. These correspond to the actual actions the player can take inside City Conquest. 90% of the gameplay boils down to building buildings, upgrading buildings, and selling buildings. Then we have the player, either 0 or 1. 0 is the blue player, 1 is the red player. Then we have the X and Y tile coordinate. Then we have some 4-letter code indicating what kind of building it is, like SKYC for skyscraper, RKTL for rocket launcher, and then an ID. So when you load in a save game or a new map in City Conquest, all it's doing is reading in this big long stream of commands and essentially executing those commands. So then when you have two players interacting at the same time, those are essentially just competing command streams is what's going on. You've got on the left side a command stream for the blue player, and on the right side you've got a command stream for player 1, which is the red player. So now, if you know anything about genetic algorithms, you're probably looking at that and saying, okay, well that's great, why can't you just take that and use those like the way you would use genes in some sort of genetic algorithm? And use standard evolutionary operators like mutation, crossover, and replacement. So then what you can do is you can take a whole bunch of random blue player scripts and a whole bunch of random red player scripts and just pit them against each other and see which ones win. And then based on which scripts win, you use replacement and crossover and mutation on those on each of the red player and blue player script populations, and in theory, you will get better and better and better scripts over time. Now, before I get any further into this, I want to make clear, this was not used for 100% of the balancing. There is a certain point where a human designer has to take responsibility, make sure that it's fun. We did a lot of manual rebalancing along with this. We also did a lot of optimization in Excel Solver. And there are also a lot of aesthetic aspects of balancing that are either difficult or impossible to quantify. And that means you can't necessarily use genetic algorithms to solve 100% of the problem. So any of these evolutionary algorithms require you to create some sort of a fitness function where you can state for any given member of the population, here's a number that indicates how successful this particular member of the population was. So the way we did that for City Conquest was at the end of any given game, only one player's capital is going to be standing. The whole point of City Conquest is you're trying to destroy the other player's capital. As soon as one player's capital dies, the other player wins the game. And then you can pretty much judge who won the game by the health of the other player's capital. If the other player is at 100% health, then it's a pretty lopsided victory. But if the other player's health is just barely hanging on, then it was probably a pretty close victory because it looks like the player who got defeated could have won if things had gone a little differently. So it essentially falls in a continuum where, at one extreme we have player A winning, the blue player, with 100% health. At the other extreme we have player B winning with 100% health. And right towards the middle we have the different cases where it's a very close game. So we can really just take that and map it to a normalized fitness function between 0 and 1 directly. So for those of you who have not written genetic algorithms before, which I think is most of you, I just want to show some real quick pseudocode to explain how it works, or at least how it broadly worked on City Conquest. I promise this will be quick. It's only 4 slides, so if reading pseudocode bores you to tears, just bear with me. So essentially what we do is we start off and we initialize the red and blue players with totally random populations. So the blue player population is this random population of maybe 400 scripts that all just have random commands in them. Same thing with the red player. Then we repeat as long as we like this function iterate genetic algorithm. This function, iterate genetic algorithm, is going to do three things. It's going to run a bunch of tournaments between the red player population and the blue player script population. Then it's going to sort the red and blue player scripts by score. You don't necessarily have to do that, but it makes the next step a little easier. The next step is to actually do the genetic operators. So now running a tournament basically works like this. We loop through the whole red and blue player populations, and they all have, every member of this population has some sort of a score value. So we loop through both populations, set the scores to 0. Then some number of times, we will come up with some random offset that's called O. Then we have some sort of a for loop. I'm calling this parallel for just to illustrate the fact that you can run it in parallel, because it essentially can work in parallel, on a parallel machine. I'll get to that later. Then we simulate a game between any given blue player script and a red player script with the given offset. And then because the score is so the score is biased so that 0 represents a lopsided victory for the blue player, 1 represents a lopsided victory for the red player. We'll add that fitness score to the blue player and subtract it from the red player's score. So essentially, in run tournaments, what we've done is we've taken our whole populations of red player scripts and blue player scripts, had each of them compete against one random member of the other population, and then figured out what is their score. Then we do the genetic operators. Basically for both the red player and the blue player, we go through the scripts. If the score is over some certain limit, then with a random chance we'll perform crossover. If it's above some other limit, based on a random chance, we'll do mutation. Crossover, you're essentially taking two population members and crossing them over at a certain point where you say, I'm going to take the first X% of this script and the last X% of this other script chosen at random, and just splice them together to create a new script. Mutation, we're essentially just taking a given command in the command stream and changing it randomly to something else. And then replacement, we're just throwing the script away and replacing it with a completely new one that we created from scratch. So that's essentially it. The basics of genetic algorithms are really, really simple. If you're curious about it, read up on, do a Google search for John Koza, K-O-Z-A, one of the creators of genetic algorithms. They've been around, I think, since the 70s or something like that. So in the case of Evolver, we managed to get this running really, really fast. When we were running the Evolver tool, we skipped the rendering, of course, because you don't need to render when nobody's looking. Optimized the game logic very heavily. We used Intel's threading building blocks to allow us trivial support for parallelism. Essentially, like I said, the whole thing runs inside a single parallel for loop. So we have all of those red player scripts and blue player scripts competing against each other in parallel. A lot of customizations to the fitness function that I won't go into here. We also ended up using the island genetic model, where essentially we are breeding different subpopulations inside the genetic algorithm that are able to evolve separately, and then occasionally sending a few of the scripts across to the other populations when things seem to get stuck. So that let us run about 1 million simulated games overnight, and it was able to run about 1 million simulations in the span of 12 to 14 hours on a spare PC. Definitely had a positive return on investment. It was a total of about 2 weeks of coding and tuning effort, so it was pretty trivial to create. And it replaced what probably would have been about 3 to 5 weeks of hand tuning, and it also gave us better results than we likely would have been able to get by hand. And most importantly, it allowed us incremental exploration of design decisions. Almost forgot. Let me show you the slides real quick of Evolver. Okay. Okay, So here's the very first screenshot of Evolver from October 9th of 2011. You can see it's all placeholder art. And you can see, so essentially what I did was I would wake up in the morning and I would take a look at the red players, what the red player scripts were and what the blue player scripts were. Again, I had a population of 400 red player scripts, 400 blue player scripts. So I could wake up in the morning and basically look at, okay, it's been running for 12 hours. What is, according to the scores, what is the very best blue player in the blue player's population? What is the very best red player script in the red player script population? Then I could take those two scripts, plug them both into the game, and watch them play against each other and see what they were doing. So that gave me really, really good feedback because I could instantly take a look and see, okay, you know, it's not building enough rocket launchers. What's going on here? You know, why is it building so many ground slammers? You know, what buildings is it favoring or disfavoring? That gave me a really strong sense of what are the dominant strategies at any given moment. All right, October 10th. Now there was one morning when I woke up and there was something really, really weird going on and I couldn't figure out what was up. I had recently added this new unit called the laser that could fire all the way across the map. And what the red player was doing is he was crushing the blue player every single time. And he was doing that by essentially like the fourth or fifth unit that he would build would be a laser that would be far off in the corner of his base. And he would build almost nothing else except for a couple little gun turrets around his capital. And I was a real head scratcher. I was like, what the hell's going on here? Then finally I realized that what the red player was doing was this really interesting strategy where these little things here are resource extractors that gather the gold and crystals you need to build things. These units here, again, crappy placeholder art, they look much better now. These are the little collector units that ferry the resources back and forth between your extractors and your capital building. Now, the collector units were not supposed to be destructible. They were supposed to be totally indestructible, and none of the units were supposed to be able to target the collectors anyway. But the red unit, the red player, through genetic algorithms, had stumbled across this strategy where it built a laser in just the right place, fired it all the way across the map. Again, the laser is the only unit that can fire across the entire map, and then hit these collector units as they were moving back and forth between the capital and the extractors. After about 5 or 6 shots, the collectors would be totally wiped out, the blue player would be starved of resources, and it would lose the game. So I thought that was really interesting, and it showed me a lot about how powerful genetic algorithms can be for really exploring the design space. So some other good examples. Here's a case where, as you can see, the gun turrets are much too powerful compared to anything else because, as you can see, it's almost exclusively building gun turrets except for that one lightning tower right near the Capitol building. Here's a case where the chiller units and the missile launchers are much too powerful because it's building those almost to the exclusion of anything else. So I found that it was very, very sensitive to you know, what the design balancing settings actually were. And anytime I would make any little change, I would very quickly see that reflected in the dominant strategies that both players used. And as I said, it was very useful for testing the incremental results of any incremental design decisions. For example, at one point I was looking at the roller unit and I was saying, okay, you know what, the roller unit, it costs 2 crystals to create that, but you know, it's kind of a low-level unit. What if I just cut the hit points in half and then charge the player only 1 crystal to build that unit instead? What would happen there? And I was thinking of the balancing in terms of the balancing of the roller unit in terms of offense and defense, but what I found was once I did that, I'm sorry I don't have any screenshots of this, what I found was once I did that, the computer player was leveraging the fact that it was so cheap to build the dropship pad for the roller, because it was only 1 crystal, that made it the cheapest building in the game, and then it could use that to wall off its base completely. And so that taught me very quickly that that was a bad approach, and that I should not make that change. Okay, so just to be clear, the Evolver system that I created for City Conquest is totally separate from the actual computer player AI in the game. As you play through the single player, you progress more and more from sort of scripted tower defense type missions to missions against actual computer opponents. And we did not use Evolver for this, and there's a really good reason for that. It was much more of a traditional AI system based on a behavior tree and sort of script-guided placement hints. I won't say it was scripted, but there was certainly a scripting system going on there to tell it more or less what types of buildings to build in which locations. It also used a behavioral mathematics approach. Here's Dave Mark's book on behavioral mathematics for game AI. I strongly recommend it if you're interested. So the reason I didn't use Evolver for the actual AI in the game is that the Evolver scripts were optimized for victory. You know, with Evolver, you want to know, what is the best possible script to win this game against the other player's, set of scripts. Whereas the computer player AI is optimized for player entertainment. You don't just want it to be challenging, you want it to be fun. Just making it hard is not good enough. So a lot of caveats, real quickly, I'll get to questions soon. It's an unusually good, this particular game is an unusually good fit for this kind of approach. It is a real-time game, but it has a discrete grid and discrete attack phases. Most games are not as easily discretized, and they're much larger in scope. The return on investment for a lot of games could be a lot lower, because a lot of them are much larger in scope and can't be discretized as easily. Programmer's time also generally is more expensive than designer's time. So if you're spending an hour of programmer time to save an hour of designer time, it's probably not worth it. You have to, get better results than that. And of course, it may be a lot easier to balance individual elements of a game than the entire game at once. You don't want to try and run all of Skyrim, for example, through a genetic optimizer. You would want to say, okay, here's some room where we're going to have, zombies versus werewolves in Skyrim or something like that, and then separately, optimize the balancing. So we're currently hard at work on City Conquest 2. Our goals, we're going to use genetic algorithms for a lot more, including mission tuning and balancing. We're going to allow customizable fitness functions for each mission. We're going to be able to pit the GA-based artificial intelligence against the actual computer player artificial intelligence. And we're going to integrate it with an external data mining system to get a lot more useful data from the results. All right, so that's it. And once again, I'm not trying to sell you a tool. I'm trying to sell you on a way of thinking about design. And the hope is, if we all really take a look at what's out there, all the current academic research and so on, then hopefully someday we'll be able to create virtual wind tunnels for game design and get to the final goal of AI-assisted game design. All right, and that's the end of my talk. Thank you very much. So I'll take questions. If you're curious to see that Shiggy video, it is up on YouTube. Just search for Shiggy, S-H-I-G-I. There are survey forms available online. Yeah, that's it. Question?
What did you use to make the slideshow? That was the best slideshow.
Yeah, what did I use to make this slideshow? It's called...
What's the best one I've seen all?
Awesome. Thank you very much. Yeah, it's called Prezi, P-R-E-Z-I. And they have a lot of... Yep. Oh, yes. So the question is, what tool did I use to actually create the presentation? And it's a tool called Prezi, P-R-E-Z-I. You can download a free version online. They've got lots of templates. The platformer scenario that I showed you was actually one of their built-in templates. Questions? Yes?
With genetic algorithms, what's the likeliness of the best solution or best strategy? There will only be one. What's the likeliness of a singularity of the answer of the best solution? Does it always lead? Does genetic?
Yeah, it doesn't. So genetic algorithms. So the question was, I'll sort of paraphrase here. What are the chances that the genetic algorithms will find the actual best solution? So there are a couple different answers to that. One is that in my game, if I do it right, there should not be one globally best solution. So it should never be able to converge on the one strategy to rule them all, right? In that one case we saw with a laser shooting all the way across the map, it did find a dominant strategy, but that was really exploiting a bug that I immediately fixed, of course, after I found that. In general, genetic algorithms, if you do them right, they will converge on something close to the optimal strategy given enough time. So, if you have it set up correctly, you will see over time it generally does a really, really good job. It's just that some problems require you to run it for an hour, some might require you to run it for weeks, and a lot of it depends on how much power you throw at the problem. Any other questions?
Trying to come up with the right equation, but for your game, what are the odds that you would, like, if you ran it now with your proper balancing stuff, will the winning AI still favor a certain type of tower, or will it be a...
No. Okay, so the question was, if I were to run Evolver right now in the game, would it favor a certain type of tower or anything like that? And the answer is no. It would ultimately converge to a solution where it had a good distribution of a lot of different kinds of towers, which is exactly, the design goal. So it's still going to lose if you take that fixed script that's non-reactive and put it against a computer player that can then see exactly what the computer player is doing and build something that is optimal against that particular strategy. But in general, you're going to see that Evolver uses a very, very good mix of all sorts of different kinds of defensive buildings and offensive units against the other player. Question?
I noticed you're using genetic algorithms mostly to test gameplay,
Mm-hmm.
and I was wondering if you've ever taken the time to use it to actually modify the gameplay.
Mm-hmm.
Like, I see you're testing a bunch of parameters with these bots more or less.
Right.
But then you have to go and change the parameters and then see how the bots.
Exactly. Yeah, so the question is, did I ever experiment with using genetic algorithms to actually change the parameters automatically? Because with the system I have, I'm using it essentially as, a playtesting tool, but then I am manually changing all the parameters based on what I am seeing the different players do. I have not, but you're absolutely right, and that's an excellent question. And in fact, one of the papers back here, I believe it is... Yeah, the paper by Alexander Jaffe, Alex Miller, and a whole bunch of other people evaluating competitive game balance with restricted play. I believe it uses an approach sort of similar to what you're talking about. So, where they're actually doing a lot of the balancing itself in, an automated system. Question?
From when you completed your genetic algorithm until the game was as balanced as the final product.
Okay, so the question was, how long was it in general between the time that I completed the genetic algorithm and until the time we actually submitted the first build to the App Store? That was about a year, to be honest. It was a pretty long time, just because we had so many missions that we had to create, and so much to build. And the Evolver was one of the first things that we built once we had the basic gameplay running, because we wanted to be sure that we could use that tool to help us balance new units that we introduced to the game and make sure that they were appropriately tuned. So, and we would literally let it run overnight, every single night, almost up until the very last few months. Question?
For your game, if you were to build an AI that was geared toward winning and reactive, would it work the same way that I've seen a couple of presentations on AI where they've got the heuristics and then make decisions, or would it, could it be as simple as they built this, so I built this?
Right. So the question is, if I were to build an AI opponent that really was optimized for victory, would I use behavior trees, things like that, or would it be a simple, case of figuring out if the opposing player builds this, then I build this? That's a really good question. I've definitely thought about, the part of the problem with the Evolver scripts right now is that they are totally fixed and static. Yeah, the Evolver scripts they're totally fixed and static. So once two players in the Evolver start playing against each other, they don't ever react to what the player is doing because they're just a linear stream of commands. So if you were putting that against an actual human player, that would be, well, it is a real shortcoming overall because it's very non-reactive. So if I were to actually optimize the computer player for victory, I would certainly use some sort of a behavior tree system. There would also be decision trees involved at some point. Yeah, there are so many different ways to tackle that. So it's hard to it's hard to list just a few. So and you could certainly build a system like Evolver where instead of building fixed scripts, you're actually evolving trees, and then those would give you the opportunity to make them reactive in different ways. So you could say, okay, branch this way in the behavior tree, if the human player has more resources if the opposing player has more resources than I do at this point in time. Or branch here if the opposing player has more than 2 gunship units or something like that. Question?
So if these scripts are complete playthroughs of the game?
Yes. Yeah, so
You said you have 800 of those, 400 scripts?
yeah, so the question was, are the scripts complete playthroughs of the game, and how many did you have? So I had a single separate test map for the Evolver. It was sort of like the Sands of Alatok map if you end up downloading the game on the App Store or Google Play and trying it out. It's basically sort of like Sands of Alatok but without all the terrain obstacles and stuff like that. So it was all done just on a single setup mission designed specifically for these opponents, and it would run about, initially I had it set up where it would run about 400 red player scripts and 400 blue player scripts against each other. After about 3 or 4 months, I switched it over to using the island genetic model, where you've got separate subpopulations. So I think what I had were like 3 separate subpopulations of about 300 scripts each. And then
Were those generated by hand, or did you have some method of generating?
yeah, I mean, well, again, they were initially generated randomly.
Okay.
Just like in here, start off with totally random scripts, and then just run the genetic algorithm. Run a bunch of tournaments, pit them against each other, and then see how they do, and then based on the result of that, do the genetic algorithm, the genetic operators like crossover, mutation, and things like that. Question in the back.
I have one thing that we got to do, but I do have a question. Is it possible to have Evolver scripts test for different results, such as draw or losses, rather than victory?
Yes. So the question was, is it possible to have the Evolver script test for different results like draws or losses instead of victories? So every time the game ends, it is a victory for one player and a loss for the other, and then the fitness score essentially takes that into account, right? Because a 0 means a total overwhelming blue player victory, a 1 is a total overwhelming red player victory, a 0.5 is a really close call for either player, where the other player just barely scraped by. And then I think we had something in there where if it was a draw and neither player, yeah, we did have something in there where if it got to like, I don't know, 1,000 turns or something like that in the game, normally they should end with one player winning, but there's some times when that doesn't happen. And in that case, I think what we did was we just compared the health of the 2 players' capitals plus like the total of the number of buildings they had built and their resources and things like that to generate a fitness score. Question?
Yeah, that's the question. So talk a bit about how you could incorporate behavior trees.
Mm-hmm.
Do you think there's a role there for using this kind of genetic algorithm to actually evolve the AI itself?
Right.
Rather than hand coding it?
Right. Yeah.
Generate a pool of AIs so you can then pull out like different AIs for difficulty levels.
Yes. So the question is, I talked briefly about the potential of using behavior trees in something like this. Is it possible to actually use those to, generate the AIs themselves? Because like I said, I did use totally separate approaches for building the computer player AI versus the Evolver, because the computer player AI was optimized much more for entertainment and also to teach the player how to play. So the answer is, the answer to that is yes, but you certainly can use genetic algorithms and things like that to tune AI systems and make them more challenging. And I think there are some cases where that can be a good idea. But whenever the subject sort of turns to that, I just sort of warn people that you can use computational intelligence techniques to make a good AI system better, but you shouldn't use it to make a good AI system in the first place, right? It's very, very important when you're developing an actual computer opponent to make sure you understand what it's doing at any given point in time, to make sure when the designer is confused by what it's doing that he can come to you and you have some way of fixing it. Don't ever rely on genetic algorithms to just automatically come up with your AI opponent, because that's generally not going to work. But if you have a good AI opponent and it's solid and it does everything that's expected of it, and you've got the time to go and say, hey, can we make this even more challenging and tune some of the magic numbers that we've put in the code, for example, using genetic algorithms, then that's a great idea. And if it doesn't work out, you can just go back to the one that you had created by hand. Was there one more question in the back?
I was going to make a quick comment that come to my talk in 15 minutes in the same room. I'll be covering that a little bit. Okay.
Great. Okay, the next talk will be covering that a little bit. So I'm looking forward to that. Any more questions? Okay, thank you very much.